Hello, today I have two problems from the 2015 FMA exam that relate to density and also harmonic motion. So prerequisites for this, you should know the spring harmonic motion. You should know definitely everything you can about fluids. The video will say more specific things. So we're given a U-Tube manometer consists of a uniform density cylindrical tube that is bent to a U-shape. It is originally filled with water that has density Pw. The total length of the column of water is L. Ignore surface tension and viscosity. The water is displaced slightly so that one side moves up a distance x and the other side lowers a distance x. Find the frequency of oscillation. Okay, so here I've drawn a U-tube. Here's the equilibrium point, and then it says it pushes it down a distance x, and then the other side moves up a distance x. So I'd say it's important to note that this is equal to 2x. And we should also know that the total length of all the water in this is equal to L, like when it goes from here to here, because then we can know how massive it is. So let me point you to this equation, which is for the period of a spring, but as it's important to note how you can use this in other situations. M is the inertial thing, it's stopping the object from moving as much, and then K is the restoring force, or gives it oscillations. So I'll start with M. M is pretty easy to calculate. We just want all the mass in the system. So we're already given that this and all of the water in here has a length L. And for the sake of it, we'll call a cross section of this. It's not given, but we'll call it A. It will cancel out anyway later. And then, because we need the volume, there's the volume. And then if we multiply it by the density, we get the mass. So we have LA, P, W. Now to find the restoring constant K, it's not very apparent in this what the K value is, or how there's a spring constant in this. But we just have to imagine K is equal to how much force there is based on how much displacement there was. Because if you did this experiment in school, maybe not this year, but the year before, you experimented with where you pulled the spring back higher amounts and you tested how much force it provided. And that's how you find the spring constant, which is the slope of this. So all we have to do is find the force over the change in distance. Well, the change in distance, we don't need to do anything for that. The force, well, there's 2x above here because of how much you pushed it. So the force would be the volume, or the mass, of how much you changed it times gravity. But this isn't the same as this m, because this is how much you displaced it. So that m would be g times 2x, which is the length. And then we have to multiply that by the cross-section. And then we have to multiply that by the density of water. And then we get 2g times the cross-sectional area times the density of water. So then we can now find the period. So t is equal to 2 pi. Let's plug in m on top. Let's let these cancel out. So a cancels out with a, pw cancels out with pw. 2 pi square root of L over 2g. Recognize that from a pendulum. So that's the period. If we want that, we take 1 over the period. So we get square root 1 over 2 pi times square root of 2g over L. And that gives us answer A. Okay, the second problem was a lot less troublesome, compared to the first one at least. Oil with density half of water is added to one side of the tube until the total length of the oil is equal to the total length of the water. Determine the equilibrium height difference between the two sides. So, two things to note here. Oil has density half that of water. PO equals 1/2 of PW. And it's added until the total length of oil is equal to the total length of water. So we have a length of L here, and we also have a length of L of water in total. So for this to be an equilibrium, both sides must have the same mass. So it's pretty easy to calculate how much mass. So oil is less dense than water. So we know that it won't be like balanced oil and water. We know that there'll be more oil, or all oil on one side, and then the water will be over here. It doesn't mix, obviously. Let's say there's some height m of water here. Well, then it's not hard to calculate how much is here. We just take the total minus the amount that we have on the other side. O minus m. And then we just calculate with the densities. So there, we have the mass on both sides of this. So cancel out all the a's, cross-sectional areas, because that doesn't matter now. What we want to solve for is m. So let's distribute everything out on the right side. On the left side, let's distribute the values. After simplifying, we get this, and then we take out the L and replace PO with 1/2 PW. Okay, so I made an error in my calculations the first time through, so I'm just going to continue this from this point onwards. We cancel out the densities, redivide 2 on this side. So M equals L over 4. Okay, and then now if we want to find this height, which is the difference between them, we take this minus that. So L plus M minus L minus M, and that is equal to 2M. And then we evaluate that, plugging in L, we get L over 2, which gives us answer choice B. And I'll let the video continue on. And we are done with these two rather pesky oscillation mixed with fluid dynamics problems. Alright, see you.